Hey folks, in this video I want to introduce you to sigma notation, or sometimes also called summation notation. Sigma, capital Sigma, is a Greek letter in which it is an operation that tells us to sum various elements or add various elements. And I want to illustrate this with some sample data in a way that you'll commonly see in our statistics courses. In this sample data, there's just 4 unique values here. And instead of writing every value in a data set every time, we often will give a data set a name. And in this example, I will call the data set Y. Furthermore, we can specify that Y is a set of values composed of 1, 2, 3, 4 values in this case, but this could go on and on and on till your last Y value. So here I've got an index I, and I is going from 1, 2, 3, all the way till n. And in this case, we have a sample of size 4, and I'll just specify n is 4 for us here. The values in our data set, we can refer to them as, this might be Y1, this is Y2, this is Y3, and Y4. So now we've got a short way to address this data set. We can call it Y. That's going to be useful in a moment when we see how we utilize sigma notation. Let's illustrate sigma notation by evaluating the following. So the Greek letter capital Sigma, right here, this is telling us to take the sum of something. However, we have yet to specify of what. And now that I've written yi, we can take the sum of all the elements in y. So what this says is take y1 plus y2 plus y3, and we've only got 4, so we're going to stop at 4. Cool, so we're going to add the values from up here, 9 plus 5 plus 4 plus -2. Excellent. Now my artistry here isn't too good. Here's what it would look like if a computer generated these symbols, but hopefully I get the point across there. Now there's a little bit more info that can go into this sigma notation. Often on the bottom of our sigma symbol, we say where the index I starts, and at the top we say where it ends. And in this case, I might as well just write n, because we know that's the entire sample size, n is 4. So down here, this is the starting position that we start our addition at. Start at I equals 1. And then this is where we stop or end our summation. This information is not necessary if you're going to add all the elements that are present. If you only want to add some of the elements present, not typical in our stats class, but if you wanted to add only the maybe last 3 values in the data set, here we're going to start at I equals 2. So we would start with the second element, which is a 5, and then we'll add the 4, and we'll add -2, which is a 7. So we won't really see this too much in our course, but that is a more complete picture of sigma notation. Let's do another example. Let's add the squared elements. Here, we want to take each value and square it before we add them. We got 81 plus 25 plus 16 plus positive 4 gets us 126. So notice this is not 16 squared, right? This isn't take the sum and then square it. If we wanted to achieve that, what we would have to write is take the sum and square the entire quantity. That is how you get 16 squared. Let's look at a common quantity that we use in statistics. See if I could fit it in over here. I want to write it down and see if you can determine what I'm talking about. Let's consider what you get when you add everything that you've got, but divide by the number in which there was. Do you know what this is representing? Isn't this the sample mean? So I didn't show you this formula in the central tendency video because we hadn't talked about this notation yet, but this is a very quick, concise way to formulaically write out the mean of a data set. While we're at it, let's compute the sample mean for our example here. So we can call this y bar, and we're going to divide by 4 after we add up all of our values. Oh, but didn't we already add these up? Don't we already know what this adds up to? That is a 16, right? So I don't need to reinvent the wheel there. What is 16 divided by 4? Our average value is a 4. Cool. We're going to use this notation quite a bit in the coming weeks, and so I want to build up the way in which we're going to utilize this formula. So I'm going to scroll down, give ourselves some space. Let's evaluate the following expression. Let's take the sum of the difference between the observations in our sample and their mean. Okay, so I can still see my sample values up here. We've got the mean also right there. So the way this is going to look is 9 minus the mean of 4 plus 5 minus the mean of 4 plus 4 minus the mean of 4. That's cool. Plus negative 2 minus 4. Now, we could go from left to right and start steamrolling this train of addition, but I want to encourage us to put these parentheses kind of like the way it's shown right here. We're going to look at these subtractions sort of as their own little piece. So now we have a sum of these subtractions. Now these actually have a name, so I'm getting us geared up for that. Now let's do 9 minus 4, we know that's a 5, plus 1, plus, ooh, that's a 0, plus -6. Can you see what these values all add up to? Check that out. That is a 0. Awesome. This summed to 0. This quantity summed to 0. This has a name. This is called the deviations from the mean. And they always add to 0. So this was not a fluke. If we had a brand new data set and a brand new mean, this would always sum to 0. Because check it out. What we did was we have the values, point to them in blue. We know those add up to 16, right? There's 4 of them. And in yellow here, we subtracted the average value 4 times, the same as our sample size. So this must always equal 0. Pretty cool. Let's do this again. Let's evaluate another expression. This time I typed this in so that way you could see how crisp it can look. And here we're going to take the sum of the deviations from the mean, but this time they will be squared. So this is going to initially look kind of like what we've got up here. But this time, these deviations need to be squared. Is the answer going to be 0 again? No way. Because this time, we're going to take these subtractions and square them. Ooh, -6 squared. Okay, so here we'll have 25 plus 1 plus 0 like that, and remember a negative multiplied by a negative gets you positive 36, and this looks like a 62. Awesome. This also has a name. This is called the sum of squares, because we just added up a bunch of squared quantities. Those are those squared deviations. And we're going to do one more calculation, which is going to get us geared up for the next section in our course. Okay, I've beefed this up a little bit for us. Let's evaluate the following. Now, it looks like I probably just went hyper mode on you, but check it out. The part that we already have worked on, I'm going to put in parentheses here. That's really the bulk of the work, and we already know what that boils down to. So all we need to do now is a square root will be the last thing, and we'll do a little division. So here it comes. This equals the square root of, our sample size was 4, so this would be 4 minus 1, which is a 3, and the value in the green parentheses there, that was 62. Not so bad. So we can divide 62 by 3 and then square root the result. I'm going to open my handy dandy calculator here. 62 divided by 3. And now we need to take the square root of that. This should be somewhere between 4 and 5. I can square root the answer. Awesome. 4.546. Cool. So we're going to see what this is in the upcoming sections of our course. This does have a name. This is called the sample standard deviation. And now that you know how to compute it, our next video will be dedicated to describing what on earth is this thing. See you there.